Good evening, Dr. Kenny. So, Group 4 will be doing an experiment about evaluation of cutting shape and size on cutting suspension in the drilling operation. So, our group consists of Akmal Reza, Adam Hakimi, Wan Arif, and myself, Rohit Eskandar. For introduction, the effectiveness of drilling operation is significantly dependent on the proper removal of rock cuttings from the wellbore to the surface. Cuttings are generated at the drill bit with the progress of the drilling process, which is after generation, rock cuttings mix with the fluid, forming solid liquid system. Failure to remove cuttings effectively can lead to major drilling problems, including stuck or plugged drill string, loss of circulation, slow rate of penetration, and formation damage. Cutting transport is influenced by the properties of drilling fluid, such as gel strength, as well as characteristic of the cuttings, including their size, shape, and density. Gravitational forces cause larger and denser cuttings to settle more quickly, while smaller particles may remain suspended for a longer period, depending on the viscosity of the drilling fluid. The irregularity of the cutting surface will lead to increased drag force and a greater flow separation phenomenon, thus reducing the settling velocity compared with spherical particles. Understanding the effects of cutting size, shape, and drilling fluid properties on cuttings transport is essential for improving hole cleaning in real drilling operations. So our problem statement is, does the shape and size of cutting influence their suspension in time in drilling fluids? Objective to examine the effects of various cutting sizes and shapes on the suspension time in different drilling fluids. And our hypothesis is, according to our prediction, larger cuttings will settle faster, resulting in a shorter suspension time. Besides that, cuttings will with irregular shapes take longer to remain suspended than regular ones because the fluid exerts more resistance on them. Lastly, fluids with higher gel strength can better hold the cuttings in place and extend the suspension time. So for our scope of study include cutting materials and sizes, which is stones, glass beads, aluminium bar, and gel strength. While for drilling fluid, which is bentonite solution and glycerin. Next,
Okay, hello, my name is Wanaria Khairuddin. Next, I will continue about the theory. So, the first is about the cutting suspension. Suspension is the ability of drilling fluid to keep the rock cutting suspend and transport them to the surface. The fine drill cutting are mixed with the drilling fluid cause the properties of the drilling fluid will change based on the cutting properties. So the larger cuts often settle quicker, resulting in shorter suspension time within the drilling fluids. Next is a gel strength. Gel strength defined as the measure of the rate of gel formation and the strength of gels developed in static condition within drilling fluids. It measures in unit of pound per 100 feet squared. So the higher gel strength helps to suspend cutting during brief pause in circulation. Next is a drag force. So the drag force is the resistance an object experience when moving through a fluid, such as air or water, and its act in the opposite direction of motion. Irregularly shaped particles may suffer more drag, extending suspension duration under certain fluid condition. So this is the drag force for the upward direction, which is F equal to 6 pi r unit for the viscosity and multiple with the velocity. And the drag force for the downward direction, this is the formula, is quite a little bit longer. And next, the equilibrium of the upward and the downward force occur at a constant for rate known as the terminal velocity. The equation of downward and upward force can be combined to determine V, which is the fall velocity, which result in a new equation for or we call it as terminal velocity. So here is the new equation. We equate with the upward and downward. However, in the experiment, the test object terminal velocity can be calculated by dividing the fluid height by the time it takes for each object to reach the bottom. So the formula is V equal to d over t. So V is velocity in meter per square, and d is in height of the liquid in the cylinder measurement in meter, and t is time taken to reach the bottom in second. So that's it.
My name is Sadam Hakimi, and I will be explaining the materials and apparatus needed for this experiment. So the materials are bentonite, glycerin, water, cuttings, which is the stone, glass bead, and aluminium bar. For the apparatus, we need graduated cylinder, beaker, spatula, rheometer, mud stirrer, measuring tape, stopwatch, and PVC pipe. So this is the first procedure. So we have to prepare 3 samples of stone, glass beads, and aluminium beads, and weigh the mass of every samples. And then we have to measure the length and area of each sample. And then we have to fill water into a beaker and drop the sample inside the beaker to obtain the bulk volume. And then we repeat the last step with different type of sample. For the next procedure, we have to prepare two type of liquid, which is bentonite mud and glycerin, and then we position a PVC pipe with a 40 millimeter diameter vertically inside the measuring cylinder and slowly pour the mud into the measuring cylinder until it reaches a volume of 2000 milliliter. And then we drop the different size cuttings, including stones, aluminum beads, and glass beads into the cylinder and record the time taken for the cuttings to settle at the bottom of the cylinder. And then we repeat all the steps using glycerin instead of bentonite mud. And finally, for the last procedure, we fill the viscometers container with with the mud we prepared earlier. And then we place the container securely on viscometer stage and set the device rotational speed to 600 rotation per minute for 10 seconds. And then we rest for 10 seconds and set the rotational speed to 3 RPM, and we take the highest deflection reading. And then we repeat step 3 and 4 using 10-minute rest. And we repeat step 1 to 5 using glycerin instead of bentonite mud. So this is the drawings for the procedure for 1, 2, and 3. Okay, next.
Good evening. My name is Akmal Reza bin Ali. So I will be explaining the expected result and the conclusion. So here we have the table for two type of sample liquid, which is bentonite, bismuth, and glycerin. We have two cylinder with different diameter, and as you can see, we have for each cutting type, we have three different size. So here is the expected result for the gel strength for the liquid. For the mud, bentonite base mud will and glycerin. For the glycerin, uh, we'll expect it to not have a gel strength since it's Newtonian Newtonian fluid. So here is the suspension time versus cutting size and drilling fluid use. As we can see from there, the as the cutting size increase, the suspension time decrease. This is due to smaller cutting having a larger surface area to volume ratio. The upward drag force is proportional to the particle radius, while the downward gravitational force is proportional to the cube or the radius, meaning that the downward force increases much faster as particle size increase as compared to drag force. Next is the suspension time versus cutting shape. Irregularly shaped particles are expected to have significantly higher suspension time since they generally will have higher surface areas for the upward drag forces to act on. Next is the suspension time versus gel strength. Fluid with higher gel strength are expected to suspend particles more effectively because the stronger gel structure resists particle movement when the fluid is static. A higher gel strength means the fluid requires greater stress for particle to break the gel network and start settling, allowing them to remain in suspension for a longer period. So, for the expected conclusion, the results are expected to support the hypothesis that smaller, thinner, and more irregularly shaped cutting will remain suspended for a longer time, while larger and rounded cuttings will settle faster in all fluid tested. drilling fluids with higher viscosity and their strength are expected to show better carrying capacity. Uh, this suggests that in order to enhance hull grinding as well as safer and more efficient drilling operation, the drilling fluid must be formulated with sufficient viscosity, jet strength, and carrying capacity, especially involving large and dense cuttings. So here are our reference. That's all from us. Thank you.